Welcome to this problem-solving session. Today, we'll dive into problem number 563, binary tree tilt. This problem challenges us to analyze a binary tree and compute its tilt, a concept that requires understanding subtree sums and recursive traversal. Let's explore approaches to solve this step by step. In this problem, we are working with a binary tree, and our goal is to calculate the sum of tilts for all the nodes in the tree. The tilt of a node is defined as the absolute difference between the sum of the values in its left subtree and the sum of the values in its right subtree. If a node does not have a left or right subtree, the sum for that subtree is considered to be 0. The tilt of the entire tree is then the sum of the tilts of all individual nodes. For the input format, we are given the root of the binary tree, where each node contains an integer value. The output will be a single integer, which represents the total tilt of the entire tree. Let's look at an example to better understand how this works. Consider the first example where the tree has 3 nodes. The root node has a value of 1, with 2 child nodes having values 2 and 3. For node 2, there are no subtrees, so its tilt is 0. Similarly, node 3 has no subtrees, so its tilt is also 0. For the root node, the tilt is calculated as the absolute difference between the sums of its left and right subtrees, which is 2, 3 equals 1. Adding these values together gives us a total tilt of 0 plus 1 is equal to 1. Now, in the second example, the tree is larger and more complex. The root node has a value of 4, with child nodes 2 and 9. Node 2, in turn, has 2 children, 3 and 5, and node 5 has a single child, 7. We'll calculate the tilt for each node step by step. For the second example, starting from the leaf nodes, node 3 has no subtrees, so its tilt is 0. Node 5 has one subtree with a single node, 7. The tilt for node 5 is the absolute difference between 0 and 7, which is 7. For node 7, there are no subtrees, so its tilt is 0. Moving up to node 2, its left subtree sum is 3, and its right subtree sum is 5 plus 7 is equal to 12. The tilt for node 2 is 3, 12 equals 9. For node 9, there are no subtrees, so its tilt is 0. Finally, for the root node 4, the sum of the left subtree is 2 plus 3 plus 5 plus 7 is equal to 17, and the right subtree sum is 9. The tilt for node 4 is 17, 9 equals 8. Adding up all the tilts, we get 0 plus 7 plus 0 plus 9 plus 0 plus 8 is equal to 24. This gives us the total tilt for the tree in this example. Now, let's consider some important edge cases. First, if the tree is empty, there are no nodes to calculate a tilt, so the output is 0. For a tree with only one node, the tilt is also 0 because there are no left or right subtrees. Node values can include negative numbers, so we must ensure that the tilt calculation always takes the absolute value of the difference. For unbalanced trees, where most or all nodes are on one side, the tilt calculation should still work correctly. Finally, for large inputs with up to 10,000 nodes, our solution needs to be efficient in terms of both time and memory usage to handle these cases without running into performance issues. To start solving the binary tree tilt problem, one straightforward approach is to use a brute force method. The intuition here is simple. For every node in the tree, we separately calculate the sum of the left and right subtrees, determine the tilt by taking the absolute difference between these sums, and then accumulate this tilt into a global variable. The steps involve recursively computing subtree sums for each node, calculating the tilt, and repeating this for all nodes in the tree. However, this comes at a significant cost. The time complexity is n squared in the worst case because, for each node, we end up recalculating subtree sums repeatedly, which involves redundant traversals. While the space complexity is h, where h is the height of the tree due to the recursive stack, the inefficiency of repeated computations makes this approach impractical for larger trees. The key drawback is the repeated recalculation of the same subtree sums, which makes it clear that we need a more efficient solution. A more efficient solution comes in the form of an optimized approach that leverages post-order traversal. The key insight here is that we can calculate subtree sums and tilts simultaneously during a single traversal of the tree. Using post-order traversal, which processes nodes in the order of left, right, and then root, we visit every node once while recursively computing the sum of its left and right subtrees. The tilt of the current node is calculated as the absolute difference between these subtree sums, and this tilt is added to a global variable that tracks the total tilt of the tree. The sum of the current node's subtree, which includes the node's value and the sums of its left and right children, is then returned to its parent node. This approach is highly efficient, with a time complexity of O(n), since each node is visited exactly once. The space complexity remains O(h) due to the recursive stack. What makes this approach particularly effective is that it eliminates redundant calculations entirely by combining tilt computation and subtree sum aggregation within the same traversal. Post-order traversal is especially suited for this task as it ensures that we process child nodes before their parent, making it possible to aggregate results efficiently. Given the options, the optimized approach using a single post-order traversal is the clear choice due to its efficiency and simplicity. By avoiding the repeated calculations inherent in the brute force method, this strategy scales well even for large trees. While both approaches have the same space complexity of O(h), the decisive factor is time complexity. The brute force method's O(n) squared runtime is impractical for larger inputs, whereas the optimized approach processes each node only once, achieving O(n) time complexity. Additionally, the implementation of the optimized approach is clean and leverages recursion effectively, making it not only faster but also elegant. While a minor trade-off is the need to carefully implement post-order traversal logic, this is far outweighed by the performance benefits. The moment of clarity here was realizing that tilt computation could be combined with subtree sum calculation in a single traversal. This insight eliminates redundant work and highlights the power of post-order traversal as a tool for solving tree-related problems efficiently. To solve the binary tree tilt problem, we first need to understand the concept of tilt for a node. The tilt of a node is defined as the absolute difference between the sum of all node values in its left subtree and the sum of all node values in its right subtree. Our objective is to calculate the total tilt of the entire binary tree, which is the sum of tilts for all nodes in the tree. The brute force solution involves a recursive traversal of the tree. The key idea is to define a helper function, calculate tilt, that will handle the heavy lifting. This function will compute the sum of all node values in the left and right subtrees, calculate the tilt for the current node, and then return the total sum of values in the subtree rooted at the current node. For the recursion to work correctly, we need a base case. If the current node is null, we simply return 0. This ensures that the recursion terminates properly and avoids errors when traversing leaf nodes. The recursive calculations form the core of our solution. For each node, we first calculate the sum of the left subtree by calling calculate tilt on the left child. Similarly, we calculate the sum of the right subtree by calling the function on the right child. Once we have these two sums, we can compute the tilt of the current node as the absolute difference between the left and right subtree sums. To keep track of the total tilt across all nodes, we use a global variable called total_tilt. Each node's tilt is added to this variable as we compute it. Finally, the helper function returns the total sum of the subtree rooted at the current node, which is the value of the current node plus the sums of its left and right subtrees. To tie everything together, we use a driver function that starts the recursion at the root node. Once the recursion is complete, the value stored in total_tilt gives us the total tilt of the entire tree. This recursive approach ensures that we visit each node once and compute all the required values efficiently. The efficiency of this solution lies in its traversal strategy. Since each node is visited exactly once, the time complexity of the algorithm is O(n), where n is the number of nodes in the binary tree. This makes the solution highly efficient for large trees. The use of a global variable for total_tilt simplifies the process of accumulating the tilts across all nodes, as we don't need to pass additional parameters through the recursion. In terms of data structures, the algorithm operates directly on the binary tree and uses recursion to traverse it. The global integer variable total_tilt is the only additional storage required. Now, let's consider some edge cases. If the tree is empty, meaning the root is null, the total tilt is simply 0 because there are no nodes to process. For a single node tree, the tilt is also 0, as both the left and right subtrees are empty. Finally, the algorithm naturally handles unbalanced trees, as the recursive function processes each subtree independently. This ensures that the solution is robust and works for all tree structures. The code implementation ties everything together. We define a helper function called calculateTilt inside the findTilt method. This function uses recursion to compute the tilt for each node. If the node is null, it returns 0. Otherwise, it recursively calculates the sums of the left and right subtrees. Using these sums, it computes the tilt for the current node and adds it to the global variable self.total_tilt. The function then returns the total sum of the subtree rooted at the current node, which includes the node's value and the sums of its left and right subtrees. The recursion starts from the root node, and once it completes, the findTilt method returns the value of self.total_tilt, which contains the total tilt of the entire tree. This implementation is straightforward yet powerful, leveraging recursion to traverse the tree efficiently while maintaining a clean and simple structure. To implement the solution for the binary tree tilt problem, we start by defining a basic structure for a binary tree node. The treeNode class includes three attributes: val for the node's value, and left and right for its child nodes, which are initialized as none by default. Next, in the solution class, we define the findTilt method, which will compute the total tilt of the tree. Inside this method, we initialize a variable total_tilt to 0, which will store the cumulative tilt of all nodes. Now, we define a helper function called subtree_sum that takes a node as its parameter and will be used to calculate the sum of all nodes in the subtree rooted at this node. If the given node is none, meaning it's a leaf node's child, we return 0 as its sum. Otherwise, we recursively calculate the sum of the left and right subtrees using the same subtree_sum function. Once we have the sums of the left and right subtrees, we compute the tilt for the current node by taking the absolute difference between these two sums. This tilt is then added to the total_tilt variable to keep track of the cumulative tilt of the entire tree. Finally, the function returns the sum of values for the subtree rooted at the current node, which is the node's value plus the left and right subtree sums. After defining the recursive helper function, we initiate the process by calling subtree_sum on the root of the tree. This triggers the traversal of the entire tree, calculating the tilt for each node and accumulating it into the total_tilt variable. Once the recursion completes, the total tilt of the tree is stored in total_tilt. We then return this value as the final result of the findTilt method. This approach ensures that every node is visited exactly once, and the tilt is calculated efficiently for the entire tree. Here, we start by defining the structure of a binary tree node using the treeNode class. Each tree node has three attributes: val for the value stored in the node, and left and right for the left and right child nodes, respectively. We also provide three constructors: one default constructor, another that initializes the node with a specific value, and a third that initializes the node with a value as well as its left and right children. Next, we move to the solution class, where we declare a private variable, totalTilt, to keep track of the cumulative tilt of the binary tree. The main method, findTilt, takes the root of the binary tree as input. It begins by calling a helper function, calculateSubtreeSum, which we'll define shortly. Once the calculation is complete, it returns the total tilt of the tree. The calculateSubtreeSum method is a private helper function that recursively computes the sum of all node values in the subtree rooted at the given node. If the input node is null, meaning we've reached a leaf node's child, the method simply returns 0. For non-null nodes, it first calculates the sum of the left and right subtrees by making recursive calls. Then, it computes the tilt of the current node as the absolute difference between the left and right subtree sums. This tilt is added to the total tilt variable, which stores the cumulative tilt for the entire tree. Finally, the method returns the total sum of the subtree rooted at the current node, which includes the node's value itself along with the sums of its left and right subtrees. This return value is used by the recursive calls higher up in the tree. Let's begin with a simple binary tree that has two levels. The input tree consists of a root node with a value of 1, and two child nodes with values 2 and 3. To calculate the tilt of the entire tree, we start at the root node, initializing self.total_tilt to 0. The function findTilt calls a helper function, subtree_sum, starting with the root node. Inside subtree_sum for node 1, we first process the left child, node 2. Since node 2 has no children, the recursive calls to subtree_sum for its left and right children return 0. The tilted node 2 is the absolute difference between these sums, which is abs, 0 to 0, equals 0. This value is added to self.total_tilt, which remains 0. The subtree sum for node 2 is then calculated as its value plus the sums of its left and right subtrees, yielding 2 plus 0 equals 2. Back at node 1, we move to its right child, node 3. Similarly, node 3 has no children, so the recursive calls return 0 for both sides. The tilted node 3 is also abs, 0 to 0, equals 0, which is added to self.total_tilt, keeping it at 0. The subtree sum for node 3 is 3 plus 0 equals 3. Finally, at the root node 1, the tilt is computed as abs, 2 to 3, equals 1. This value is added to self.total_tilt, updating it to 1. The total subtree sum for the entire tree is 1 plus 2 plus 3 equals 6. The final output for this example is self.total_tilt equals 1, which represents the total tilt of the tree. Now, let's examine another example with a skewed tree structure. Here, the root node has a value of 4 and only a left child with a value of 2. Node 2, in turn, has two children, 3 and 5. As always, we start at the root node, initializing self.total_tilt to 0. The subtree_sum function is called for node 4. Inside this function, we first process the left child, node 2. For node 2, we begin with its left child, node 3. Since node 3 has no children, the recursive calls to subtree_sum for its left and right children return 0. The tilted node 3 is abs, 0 to 0, equals 0, which is added to self.total_tilt, leaving it at 0. The subtree sum for node 3 is 3 plus 0 equals 3. Next, for node 2, we process its right child, node 5. Like node 3, node 5 has no children, so the recursive calls to subtree_sum for its left and right children return 0. The tilted node 5 is abs, 0 to 0, equals 0, which is added to self.total_tilt, keeping it at 0. The subtree sum for node 5 is 5 plus 0 equals 5. Now, we compute the tilt for node 2. The left subtree sum is 3, and the right subtree sum is 5, so the tilt is abs, 3 to 5, equals 2. This value is added to self.total_tilt, updating it to 2. The total subtree sum for node 2 is 2 plus 3 plus 5 equals 10. Returning to the root node, node 4, we process its right child, which is null. The subtree_sum call for the null child returns 0. The tilt for node 4 is computed as abs, 10 to 0, equals 10, which is added to self.total_tilt, resulting in a total tilt of 12. The subtree sum for the entire tree is 4 plus 10 plus 0 equals 14. The final output for this skewed tree is self.total_tilt equals 12. Finally, let's consider the simplest case, a binary tree with only one node. The input tree consists of a single node with a value of 1. Starting at the root node, we initialize self.total_tilt to 0 and call subtree_sum for node 1. Since node 1 has no children, the recursive calls to subtree_sum for its left and right children return 0. The tilted node 1 is calculated as abs, 0 to 0, equals 0, which is added to self.total_tilt, leaving it at 0. The subtree sum for node 1 is 1 plus 0 equals 1. With no other nodes to process, the final output for this single node tree is self.total_tilt equals 0. The time complexity of this algorithm is O(n), where n represents the number of nodes in the binary tree. This is because the algorithm involves traversing each node exactly once during the recursive computation of subtree sums. Let's break this down further. First, the subtree_sum function is a recursive function that visits every node in the tree using a postorder traversal. For each node, the function is called on its left and right children, ensuring each node is visited once. This gives us a total of n recursive calls. Additionally, at each node, the algorithm performs a few operations. It computes the sum of the left and right subtrees, calculates the tilt as the absolute difference between these sums, and adds the tilt to the total. Each of these operations takes constant time, or O(1). Since every node is visited exactly once and only O(1) work is done per node, the overall time complexity is O(n). The space complexity of this algorithm is O(h), where h is the height of the binary tree. This is primarily due to the space required for the recursive call stack. During the recursive traversal, the depth of the call stack corresponds to the height of the tree. In the case of a balanced binary tree, the height is proportional to log n, resulting in a space complexity of O log n. However, in a skewed binary tree, where nodes are arranged in a single line, the height becomes O n, leading to a worst-case space complexity of O n. Apart from the call stack, the algorithm uses minimal additional space. Variables like total underscore tilt, left underscore sum, and right underscore sum require only constant space, or O1. Therefore, the overall space complexity is dictated by the height of the tree, making it OH. To further analyze the algorithm, we can look at the best, average, and worst cases. In the best case, where the tree is perfectly balanced, the height is O log n, so the space complexity is O log n. The time complexity remains O n, since every node is visited once. For the average case, which assumes a moderately balanced structure, the height is still approximately O log n, leading to a space complexity of O log n, while the time complexity continues to be O n. In the worst case, where the tree is completely skewed like a linked list, the height equals n, resulting in a space complexity of O n. The time complexity, however, remains constant at O n, as each node is traversed just once regardless of the tree's structure. When comparing this solution to a naive approach, the efficiency of the current algorithm becomes clear. A brute force method might involve multiple traversals of the tree to compute the tilt for each node, leading to a time complexity of O n squared. This is because for each node, calculating the sum of its left and right subtrees would involve separate traversals, requiring O n work per node and resulting in O n squared work overall. In contrast, the current solution uses a single traversal of the tree to compute both subtree sums and node tilts simultaneously. This reduces the time complexity to O n. The space complexity, O h, is also optimal for recursive tree traversals, as it only depends on the height of the tree. By using a post-order traversal, the algorithm efficiently computes the total tilt of the binary tree in O n time and O h space, making it the optimal solution compared to less efficient approaches. When solving the binary tree tilt problem, there are a few common mistakes to watch out for. First, a major source of inefficiency is recomputing the sums of left and right subtrees multiple times for each node. This happens when the same calculations are redundantly repeated, leading to an increase in time complexity. To avoid this, you can use a post-order traversal, which allows you to calculate subtree sums in a single pass. Another mistake is neglecting edge cases, such as an empty tree or a tree with only one node. For an empty tree, your solution should handle it gracefully without errors, and for a single node tree, the tilt should always be 0. Additionally, it's important not to confuse the global tilt of the entire tree with the tilt of the root node. The tilt of the tree is actually the sum of tilts at all nodes, not just the root. Lastly, in languages like Java or C++, be mindful of integer overflow when working with large subtree sums. Using a data type with higher capacity, such as long, or carefully checking constraints can help prevent overflow issues. Another common issue arises from using the wrong traversal order. For example, preorder or in-order traversal processes nodes before all the necessary subtree information is available, leading to incorrect tilt calculations. Post-order traversal, on the other hand, ensures that you have the subtree sums ready before computing the tilt for the current node, making it the correct choice. From an interview perspective, this problem is a great way to showcase your understanding of tree recursion and post-order traversal. It's also an opportunity to explain the inefficiencies of a brute force approach, which has a time complexity of O n squared, and demonstrate how optimizing to O n eliminates redundant computations. Beyond the algorithm, this question can also be tied to real-world scenarios, where hierarchical data analysis often involves recursive calculations. Lastly, clear communication is key. When explaining your solution, make sure you articulate the distinction between local tilt at a node and the global tilt of the entire tree to avoid any ambiguity. This problem shares similarities with several other tree-related problems that you may encounter. For example, problem 543, the diameter of binary tree, also uses post-order traversal to calculate the maximum diameter of the tree. Similarly, problem 124, binary tree maximum path sum, involves finding the maximum path sum in a binary tree and relies on comparable traversal techniques. On the simpler side, Problem 104, Maximum Depth of Binary Tree, helps build a foundational understanding of tree traversal concepts. Another related problem, Problem 110, Balanced Binary Tree, checks whether a tree is height balanced, which also depends on post-order traversal. In addition to these related problems, it's worth considering alternative approaches to solving the binary tree tilt problem. The brute force approach involves calculating the sum of left and right subtrees separately for each node and then computing the tilt. While straightforward, this method has a time complexity of O(n) squared, because subtree sums are computed repeatedly. As a result, it is highly inefficient for larger trees. A more efficient solution involves using an optimized post-order traversal. Here, you compute subtree sums and node tilts simultaneously in a single traversal, reducing the time complexity to O(n). This approach processes each node only once, which makes it much faster than the brute force method. However, it does require maintaining a global variable or an equivalent mechanism to keep track of the cumulative tilt of the tree. Alternatively, you could use an iterative approach with a stack to perform post-order traversal. This avoids the risk of stack overflow that can occur in recursive solutions, especially with very deep trees. However, while iterative methods share the same O(n) time complexity, they are often more complex to implement and less intuitive compared to recursion. Choosing between these approaches depends on your problem constraints and your comfort level with recursion versus iteration. That wraps up our discussion on the binary tree tilt problem. We covered the recursive approach to calculate the tilt efficiently, along with its complexity analysis. Remember to practice similar tree problems to sharpen your skills. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!